Good evening and welcome to this video for level 3 momentum, and this is for level 3 physics for the standard level 3 mechanics. Alright, so first things first, what is momentum? So momentum is simply a measure of the quantity of motion. So we should have covered momentum in level 2 physics. So momentum is simply the measure of the quantity of motion. Linear momentum is defined as the mass times the velocity of an object. So P equals to mv, while the angular momentum is defined as the rotational inertia times the angular velocity. In that case, it's L, which is the angular momentum, is equal to I, rotational inertia, times omega, which is the angular velocity. However, in this video, we'll be focusing on the linear momentum. Alright, so linear momentum. So linear momentum is defined as the mass times the velocity of an object. So that's P equals to mv. So any object that is moving, which has mass, will have a momentum. So linear momentum has both size directions. So for example, that could be 60 kilogram meters per second. Kilograms meters per second is the unit for momentum. So for example, 60 kilograms meters per second to the right. So the magnitude would be 60, and the direction would be to the right. So linear momentum is always conserved if there are no external forces acting on the system. So that is the law of conservation of momentum. So if we have a system and there is no external unbalanced forces, then therefore the momentum will not change. Alright, so calculate momentum. So you have a simple example here. So Kevin is running at a constant speed of 6 meters per second. Given that his mass is 80 kilograms, calculate the magnitude of his linear momentum. So I'll give you some time to work out this question. Alright, so to calculate the magnitude of its linear momentum, we need to use P equals to mv, which in this case the mass is 80 times the speed, which is 6, and that will give us a final answer of 480 kilograms meters per second, and that's our final answer. Alright, so the law of conservation of momentum, so as we stated previously, conservation of momentum states the momentum of a system is always conserved, assuming there are no external forces acting. So therefore, what that means is momentum before something happens is equal to the momentum after something happens, given that during this process there are no external unbalanced forces. Alright, so here's a practice level 2 question. So this is what we would have done last year. So here's an example. Kevin is still running at 6 meters per second, mass 80 kilograms, and collides with Matthew, who is standing stationary at the side of the road. As a result, Matthew moves after the collision. Matthew moves in the same direction as Kevin at 3 meters per second. His mass is 75 kilograms. Assuming no external forces were acting on the system, calculate the speed and direction of Kevin after the collision. So I'll give you a couple of, you can take some time to work out the answer to this question. And when you're ready, keep watching the video to find out the answer. Alright, so in this question, we're going to utilize the conservation of momentum. So in this case, conservation of momentum would apply to the system because the collision between Kevin and Matthew, that is an internal force rather than external forces. Therefore, there are no external unbalanced forces, assuming that friction is negligible in this situation. So in this case, momentum is conserved. So that's the initial momentum before the collision is equal to the final momentum after the collision. Right, so the initial momentum, that's the initial momentum that is equal to 6 times 80. That's the momentum of Kevin because Matthew was stationary at the start. And that's equal to 480 kilograms meters per second, 80 times 6. So therefore, because Matthew was stationary, our initial momentum is 480 kilograms meters per second. Our final momentum is equal to the momentum of Matthew plus the momentum of Kevin, since the question tells us that they're moving in the same direction. Therefore, 480 equals to 75 times 3, because Matthew is moving at 3 meters per second, plus of Kevin's mass times this velocity, which we're trying to figure out. If we rearrange the formula for v, we should find that the v is 3.19 meters per second, and that's in the same direction as Kevin was running initially. Alright, so momentum of a system. So a system is defined as considering one or more objects with mass as a whole. The momentum of a system is defined as the sum of the momentum of the individual objects in the system. So the momentum is equal to all the sum of the individual momentums of each of the objects in the system. So that's our P of our center of mass equals to the sum of the momentums of all the individual components in the system, all the individual objects in the system. Since momentum is a vector quantity, it has both size and direction. The individual momentums should be added using a vector addition because it's a vector quantity. The final answer should contain both the magnitude of the momentum and the direction unless specifically stated by the question. Alright, so here's an example. Okay, Kevin is running at 9 meters per second north, his mass is 80 kilograms, while Matthew is 75 kilograms, runs at 6 meters per second east. Considering Kevin and Matthew as a system, what is the momentum of the system? Okay, so I apologize for this chunk of answer here, but just try to work out the answer. So I need both the direction, so that's the angle, and the magnitude of the momentum of the system. Alright, so in this case, okay, so when you approach these questions, it's always a good idea to draw out the vector diagram. So you draw out the vector diagram. In this case, Kevin is running 9 meters per second north, 80 kilograms. His momentum is 9 times 80, which is 720 kilograms meters per second. Meanwhile, Matthew runs at 6 meters per second east. 75 times 60 is his momentum, which is 450 kilograms meters per second. Alright, so in this case, we have a right angle triangle since north and east are at right angles to each other. Therefore, we can apply Pythagorean theorem to find out the momentum of the system, the momentum of the center of mass. In this case, we can just say that 720 squared plus 450 squared square root is equal to the momentum of the center of mass. In this case, we'll get that answer equals to 849 kilograms meters per second. However, we also need the angle, which is the direction. The direction would be simply you need to find the angle. So once again, we can use our trigonometry rules. So we can say that tan of theta, tan of phi equals to 450 over 720, and therefore that should give us an answer of 32 degrees. So the way we label the direction is north 32 degrees east, because if we're looking at this angle on the left, on the bottom left hand corner here, this angle, okay, we have a north, and then we go 32 degrees towards the east, and that's where we hit our momentum of our center of mass, and therefore that will be our final answer. So the direction would be north, 32 degrees east. Alright, so movement of the center of the mass. So the movement of center of mass will always be moving at a constant speed, given that the individual objects in the system are not acted upon in external unbalanced force. In the last example, the momentum of the center of mass is 849 kilograms meters per second, and the velocity of the center of mass will simply be the momentum of the center of mass divided by the total mass of the system. So the center of mass will always be moving in the same direction with the same magnitude, given that there are no external forces acting on the system, so that will always be the same. So in this case, we try to find the VCOM for our previous question. That will simply be 849 kilograms meters per second divided by the total mass of the system, which is 75 plus of 80. That should give us an answer of 5.48 meters per second, and that's the same direction as the momentum because momentum is the vector quantity. So that will be north 32 degrees east. As the velocity of the center of mass will be constant as long as there are no external unbalanced forces on the individual components in the system. Right, so previously in level 2, we've been looking at a lot of the 2-dimensional conservation of momentum. So that's just the direct left and right collisions between objects. But in this case, we're going to be considering objects that are colliding at angles now. Okay, so we're no longer looking at just up or down or left and right. We're going to be looking at a 3-dimensional conservation of momentum. 3D conservation of momentum states that the momentum of a system will be conserved if there are no external forces acting. 3D conservation of momentum involves finding the initial momentum of a system. So this will usually be a vector quantity because momentum itself is a vector quantity. The magnitude and direction of this vector must both be considered, once again, because it is a vector quantity. This means that the final momentum will also be equal to the initial momentum, assuming there are no external unbalanced forces acting on the system. And so here's an example question. Kevin is running east at 4 meters per second. His mass is 80 kilograms. He collides with a loose stationary garbage bin, and they travel off at a 90-degree angle. So they travel off at right angles to each other. The mass of the garbage bin is 10 kilograms, and its speed is 5 meters per second after the collision. Find the speed of Kevin after the collision. Right, so here's our 2 diagrams to help you with your calculation. So in this case, we have our initial momentum. That will be equal to Kevin's momentum, which is he was running 4 meters per second and his mass is 80 kilograms, so the initial momentum will be equal to the momentum of Kevin plus the momentum of the loose stationary garbage bin. But in this case, it's a stationary garbage bin, which means that it has no momentum because it's not moving. The quantity of the motion is 0 kilograms meters per second. Therefore, the momentum of the center of mass of the system is simply equal to the momentum of Kevin, because he is the only one that is moving in this case. After the collision, okay, so we are told that Kevin and the garbage bin move off at 90-degree angles. We have displayed that in diagram number 2. So the garbage bin and Kevin, they form a 90-degree angle. And we know that the speed of the garbage bin after the collision is 5 meters per second, and its mass is 10 kilograms. So now we're going to be asked how to, we need to find the speed of Kevin after the collision. So pause the video and give this question a try, and when you're ready to see the answer, keep watching the video. Okay, so for this question, okay, it's always good to be able to draw the vector diagram. So we know that since the collision between Kevin and the garbage bin, they're both part of the system, this is an internal force and not an external unbalanced force. Therefore, we can say that the initial momentum of the system is equal to the final momentum of the system. So in this case, our initial momentum is equal to our final momentum. So I just put our initial momentum will stay the same, which is the same momentum of Kevin, which he was running at 4 meters per second, okay? And that will be equal to the momentum of Kevin plus the momentum of the garbage bin after the collision. This is because after the collision, both the garbage bin and Kevin both have momentum, and in order to find the combined momentum, we need to use a vector addition. So by using the vector addition, we should see that the momentum of Kevin plus the momentum of the garbage bin is equal to the initial momentum, which was equal to what Kevin was running at the start. So here, the reason that this vector diagram can be used is because the initial momentum of the center of mass of the system is simply equal to momentum of Kevin. So that's what I was just saying. This is because the garbage bin is initially stationary. So in this case, our initial momentum is equal to the mass of Kevin times the velocity of Kevin. That is 80 times 4, which is 320 kilograms meters per second. We know that the momentum of the garbage bin, so the magnitude of the momentum of the garbage bin is equal to its mass times its velocity, which is 50 kilograms meters per second. In this case, we know that since Kevin and the garbage moving off at 90-degree angles, we can apply our Pythagoras theorem in order to find their combined momentum, which is equal to the initial momentum. So therefore, by applying Pythagorean theorem, we should find that the momentum of Kevin is equal to 316.07 kilograms meters per second. Therefore, we can find the speed of Kevin by simply dividing his momentum by his mass, which we should get the answer of 3.95 meters per second. And that's our final answer. Alright, so example 2. Two cars are driving, so car 1 is driving east at 28 meters per second, and car 2 is driving north at 19 meters per second. The cars collide with each other and they move off at right angles to each other. The mass of both cars is 3 tons, and one rebounds at 22 meters per second, and car 1 rebounds at 22 meters per second. Find the velocity of car 2. So here are some diagrams to help you out. Okay. So in this case, the initial momentum is equal to the momentum of car 2 plus the momentum of car 1 as a vector addition. That gives us our initial momentum of the center of mass of the system. After the cars have collided, assuming there are no external unbalanced forces, it's an internal force, the collision, the momentum is conserved, which means that the initial momentum we calculated at the start will be equal to the final momentum with the collision. So in this case, since the question tells you that they're moving off at right angles to each other, we can say that the momentum of car 2 plus the momentum of car 1 equals to our initial momentum. So once again, give this question a try, and when you're ready, keep watching the video to find out the answer. Whereas for this case, once again, we're going to be drawing out our vector diagram, okay? So once again, we have our the center of mass momentum, which is the same as the initial momentum of the system, and the momentum of car 2 plus the momentum of car 1 is equal to the initial momentum. So in this case, our initial momentum, okay, of car 1 is 28 times 3,000, because 3 tons is equal to 3,000 kilograms. That should give us an answer of 84,000 kilograms meters per second. Likewise, for car number 2, its initial momentum is 19 times 3,000, which is equal to 57,000 kilograms meters per second. Because they were moving at right angles to each other, we can use a simple vector addition in order to find out the momentum of the center of mass. That is applying the Pythagorean theorem. And we should get an answer of 101,514 kilograms meters per second as our final momentum for the center of mass. Alright, so in terms of finding the speed of car 2 after the collision, we're going to be using that the final momentum is also equal to this momentum of the center of mass, which is 101,514 kilograms per second, and in the same direction. So we know that after the collision, the momentum of car 1 is equal to its velocity times its mass, which is equal to 66,000 kilograms per meter per second. Therefore, the momentum of P2 should be equal to 101,514 squared. That should be minus, I don't know why it's plus there. It should be minus 66,000 squared, and that should give us an answer of 77,130.36 kilograms per second. And that's the momentum of car 2 after the collision, and we can find its speed by dividing by the mass, which we were told is 3,000 kilograms. By doing so, we should find our final answer for the velocity of car 2, that is equal to 25.7 meters per second. Alright, that's it for momentum. Okay, I hope you enjoyed this video, and if you enjoyed the video, please smash the like button, and if you have any comments, please leave it down in the comment section below, and I'll see you all in the next one. Thank you, bye.